So, hi everyone, welcome to another edition of zkStudyClub. It's been a while. Today we're excited to welcome back William Wang, who's been a repeat guest here on the channel. So thank you, Will, for coming back to talk about ARC, Accumulation for Reed-Solomon Codes. So the work done together with Benedict Bunce from NYU, Pratush Mishra from Penn, and Wilson Nguyen from Stanford. Thank you, William. Take it away. Up to you.
Cool. Yeah. So I just want to say, first of all, it's great to be back. This work is kind of a follow-up to the previous work that we talked about in like a year ago, I want to say, at zkStudyClub. But here we kind of resolved the main limitation that was there. And yeah, let's just get started. Oh, and one more thing, just feel free if you have questions to just unmute yourself and ask at any time through the presentation. I'll just pause. Okay, cool. So let me just first start with a very high-level motivation. So kind of our overarching goal is to build IVC and PCD. So these are cryptographic primitives that have a lot of applications, including in blockchain systems like rollups, zkVMs, and also more abstractly things like parallelized and/or low memory proving. Okay, so as of today, kind of the most efficient IVC and PCD is built from accumulation schemes. These are also known as folding schemes. And I should point out that kind of when you're building IVC and PCD, there's always this baseline solution, which is to use recursive snarks. And so whenever I talk about accumulation or folding, kind of implicitly, I'm assuming that we're talking about some sort of non-trivial accumulation scheme that does better than a snark would. Okay, so accumulation schemes are typically based on some sort of group-based or lattice-based cryptography, where they take advantage of the underlying mathematical structure of the assumption. And in this work, we're going to be looking at how to build hash-based accumulation. And our approach works for many different constraint systems. In this talk, I'll just focus on R1CS. Okay, so why is hash-based accumulation useful or interesting? Well, there's, I think, two main reasons. One is it's arguably a much more conservative assumption than a lot of these other public key assumptions. It's also post-quantum secure. And the second reason is that we can kind of hope to achieve some of the benefits that normal hash-based proof systems have, specifically like a very fast prover. Okay. And I should also mention that in our previous work, we also look at building hash-based accumulation, but we kind of have this unfortunate restriction, which is that we can only achieve like a weaker form of accumulation, which we call bounded depth accumulation, which kind of hinders the practical efficiency of that work. So here we're actually just focused on building a standard full-fledged accumulation scheme that has unbounded depth and is also hash-based. Okay, so this is really the last time I'll mention IVC, and from now on, I'll kind of focus on accumulation schemes as the sort of central object of interest in this talk. So what is an accumulation scheme? I think it's just helpful to view it as a pair of reductions. So you have an initial reduction, which takes your relation of interest, let's say your favorite NP-complete relation like R1CS, and converts it into a statement for a central relation, which I've called R here. And the second component is a many-to-one reduction, which takes multiple statements in R and compresses it into a single statement in R. Okay, so the way that you would actually see accumulation scheme in action is, let's say you have some R1CS instance, you're going to use the initial reduction to convert it into like a central instance. And then you're going to repeatedly compress it with an existing like running instance. And you can do this over and over again, right? So if I have a new R1CS instance, I first convert it into R, and then I compress again. And I can do this for an unbounded number of times. Okay, and just for some context, in a folding scheme like Nova, for example, the central relation here is what they call relaxed committed R1CS, which in some sense is basically equivalent to R1CS. And so for Nova, kind of this initial reduction is trivial. And really, you would be talking about this many-to-one reduction as the folding scheme. Whereas for us, I think it will be useful to explicitly distinguish between these two components of the accumulation scheme. Okay, so I've been talking about reductions, and now I want to formally define what an interactive reduction is. So an interactive reduction is from one relation R to another relation R prime. And it's an interactive protocol between a prover and a verifier. So the prover receives some statement, and the verifier receives the instance. And they engage in some sort of interactive protocol such that at the end, the prover outputs a new witness and the verifier outputs a new instance. And just like in interactive proof or an interactive argument, there are two key properties. So the first is completeness. If the original statement was in the relation, then the new statement will be in the new relation. And the second property is soundness, which basically says if the original statement is not in the language, then the new statement will also not be in the language with high probability, no matter what a malicious prover might try to do. Okay. So in this work, we consider a very closely related model, which we introduce and call interactive oracle reductions. So intuitively, you can imagine that interactive oracle reductions are sort of the reduction version of interactive oracle proofs, where the verifier, instead of reading the prover's message in full, now gets to query the prover's messages at very specific locations. And this allows the verifier to be succinct in the overall proof length. Okay, so the cool thing in an IOR is that the instances themselves can also have oracles inside of them that the verifier can query. And additionally, the verifier can output oracles as part of the new instance. So these oracles must be selected from one of the prover's message oracles or maybe the old instance oracles. Okay, and IORs can be compiled into standard interactive reductions, essentially by using Merkle commitments. And this is analogous to how IOPs can be compiled to succinct arguments using like the BCS transformation. Cool. So now that I've defined the model, I just want to give a quick overview of what I'm going to be talking about in the rest of this presentation. So our goal will be to kind of construct interactive oracle reductions for accumulation schemes, which minimize the query complexity of the verifier. And this sort of translates into a more efficient accumulation verifier and hence a more efficient IVC scheme. So as a stepping stone, we're going to first construct a many-to-one interactive oracle reduction for Reed-Solomon proximity claims. I'll define what a proximity claim is in the next slide. And the key feature of our reduction is that the verifier makes O of lambda queries, where lambda is the security parameter. Now, in contrast, the best-known Reed-Solomon proximity tests, like STIR and WER, make O of lambda times log n queries. So we're shaving this factor of log n. In practice, so obviously it depends on how you set the parameters, but in practice, this can be quite significant. And I should say that an IOR for proximity claims is different from a proximity test in that it performs a different, it has a different guarantee. But in the context of accumulation, their verifier efficiencies are comparable because they both translate into what the accumulation verifier would look like. Okay. I should also mention here that there's also two concurrent works, I think they're called Boyle and Deepali, that also show this sort of stepping stone result. And our main result is that we construct a full-fledged hash-based accumulation scheme for R1CS, but I'll get into that later and give some comparisons at the end of the talk. Okay, so let's just focus on
what were those concurrent works again?
One is called Boyle, B-O-I-L, and the other one is called Deepali. And they both also make this odd observation that you can get a many-to-one interactive oracle reduction for Reed-Solomon proximity claims where the verifier makes O of lambda queries. Yeah. Okay, so yeah, so for now, let's focus on the stepping stone and then we'll get to like the main result afterwards. So first of all, just for some background, I want to define what a Reed-Solomon proximity test is and what a Reed-Solomon proximity claim is. So just laying out some notation, I'm going to let C be some arbitrary Reed-Solomon code, and then I'm going to let F be some arbitrary vector. So you can think of this Reed-Solomon code C as a subset of the set of all possible length n vectors. In particular, it will be a linear subspace. Okay, and the goal of a Reed-Solomon proximity test is to verify a proximity claim that F is delta close to C. That's what this notation means. And in words, basically, I'm saying there exists a code word in the subset C, the Reed-Solomon code, which disagrees with F at most a delta fraction of points. So if we set delta to be like 1/4, then I'm saying that there exists some code word C which agrees with F on at least 75% of points. So they're close in terms of Hamming distance. Okay, and Reed-Solomon proximity tests are a very common object in the proof systems literature. So some pretty well-known examples are, of course, Fry, and more recent ones like Stir and Were. And they're used to construct snarks essentially by this recipe. So you first have your NP relation of interest, like R1CS, and you have some initial reduction which converts it into a Reed-Solomon proximity claim. And then afterwards, you run the Reed-Solomon proximity test to verify the Reed-Solomon proximity claim. So really, the snark recipe can be thought of as having two ingredients, the initial reduction and then the proximity test. Okay, so for us, when I talk about Reed-Solomon proximity accumulation, what I'm talking about is a many-to-one reduction for Reed-Solomon proximity claims. And the hope is that this reduction can be cheaper than a proximity test, right? The fact that it's cheaper means that we can get more efficient, like a non-trivial accumulation scheme. And this is what the accumulation recipe would look like. So we have R1CS instances, we use the initial reduction to convert it into Reed-Solomon proximity claims, and then we just repeatedly compress it using our many-to-one reduction for the proximity claims. Okay. And I should note here that all of these proximity bounds, these delta values, are the same. And I'll refer to this as like a distance preserving reduction. So whereas in our previous work, accumulation without homomorphism, delta kind of degrades over time. So delta becomes delta minus epsilon minus 2 epsilon with every step. And this is what leads to this restriction of having a bounded number of accumulation steps. Here, our distance bound of the proximity claim will always be delta, and therefore we can continue to accumulate as much as we'd like. Okay. So let's take a look at how we can construct this many-to-one reduction. So for our first attempt, we have a prover and verifier. The verifier receives as input the two input vectors F0 and F1. And the natural strategy would be to do some sort of batching of the proximity claims. So this is a very common technique. The idea is that the verifier will just sample a random challenge alpha, and then it will output the random combination of F0 and F1 under alpha. Okay, so let's quickly analyze this. For completeness, like if these two input vectors are indeed code words, then since the code is linear, their random combination will also be a code word. So we're happy. And for soundness, if either of the inputs are far from the code, then Reed-Solomon codes exhibit this property, which is called a proximity gap. And basically, this proximity gap guarantees that with high probability, right, over the choice of alpha, the random combination of, this should be F0 and F1, the random combination will be delta far from the code. Okay, and so that's good as well. So we've satisfied both completeness and soundness. But there is a problem, which is that we haven't really shown how the verifier outputs this new vector G. So clearly the verifier cannot literally compute G itself because it needs to be succinct, and the length of G is just too long. Instead, what the verifier can do is it can output the two instance oracles like F1 and F2, or I should say F0 and F1, as well as the scalar alpha. And this virtually defines G in the sense that whenever you would query G, you can just query F0 and F1 at the same location and then compute the combination locally. Now, the issue is that this is not allowed in accumulation, intuitively because now the size of this new instance is 2 vectors. And if we continue this process of accumulating more and more things, the number of vectors, the size of the material in this instance G will continue to grow over time. And in some sense, we have not actually achieved any sort of compression. because our instance is virtually defined over many things. And this is not allowed in accumulation schemes. So to get around this issue, we're going to rely on this very common technique in Reed-Solomon proximity tests, which is called quotienting. So quotienting originated from the DeepFry protocol, and now it's used elsewhere, such as in stir and here. So I've explicitly defined quotients here. So given some vector f and some scalars xy, we say that the quotient of x under xy is also a vector, and it's defined according to this equation. So I don't want to go too much into the specifics, but for completeness, basically we can observe the following. Given a valid code word, a valid Reed-Solomon code word, the quotient of f under x and its evaluation at x will always be in the code for any choice of x. And for soundness, we have this observation that given an arbitrary vector f, letting u be the code word, which is uniquely delta close to f. Here I'm assuming that delta is at most the unique decoding radius of the code. If u of x is not equal to y, then the quotient will be delta far from the code. Okay. And quotients also generalize to more points. So if I can quotient f by a bunch of xi, yi points, and if u disagrees with any of the xi, yi, then I get that the quotient is delta far from the code. Cool. So the way that we're going to use quotients in our protocol is loosely inspired by stir. So stir also uses quotients. And the intuition in both cases is that we're going to translate a proximity claim about a virtual combination of vectors, like we had in the many-to-one reduction. And we're going to convert it into a proximity claim about a single vector, which is amenable to repeated accumulation. So the idea is that the prover is going to actually recommit to this random combination f. And then the verifier is now going to quotient f by some points xi, yi to define the new instance. And these points, the xi are obtained by randomly sampling locations in the vector. And then the verifier actually queries f0 and f1 to compute what yi should be. Okay. And yeah, the output claim is that this new quotient g is going to be delta close to the code. Okay, and I should note that stir also uses this sort of recommitting strategy, but in some sense for a qualitatively different reason. In stir, you kind of recommit over a larger domain, and they do this to kind of improve the efficiency of their proximity test. Whereas for us, we're just recommitting over the same domain. And the only reason why we care about this is that we need to actually achieve some form of compression. This is necessary in accumulation. And it's actually very important that we recommit over the same domain, because this is what allows us to kind of uniformly continue to accumulate more and more things. Okay, so let's take a look at how batching and quotients can be used together to give us our final many-to-one reduction. So it's the same setup as before.
Could I ask a question, please? Sorry.
Sure. Yep.
Sorry, just go back a slide real quick.
Yep.
Okay, so verifier defines quotient G, but G is still virtual and depends on F0 and F1, right? So how have we made progress?
Yeah, so you're right that G is virtual, but G is virtually defined only over F, not F0, F1.
Well, prover recommits to...
Yeah, so this F is now sent as a new oracle. And the quotient is now defined over a single oracle, which means that it's...
Oh, quotient's F by X and Y, but the X's and Y's come from F0 and F1. But,
yeah, exactly.
But F is the recommitted thing. Okay. Interesting.
Yeah.
Right.
Yeah, I mean, I think it'll also be clear with this visual. So the verifier samples the challenge. Now the prover is, going to send over the claimed random combination as a new oracle F. So at this point, we don't actually know, like for a dishonest prover, we don't actually know if F is equal to the random combination or not. But we're going to use this quotient to somehow enforce consistency between F and the random combination. The verifier is going to randomly choose a bunch of indices. It's going to query the original oracles at those indices. And then it uses this information to output the quotient G. Okay. And again, G is virtually defined over the new oracle F. So if we analyze this protocol, oh, go ahead.
How big are the x1 to xt?
Oh yeah, so T here, I probably should have clarified this. T will be kind of linear in the security parameter. So you can think of T as lambda.
I see.
Okay. So for the analysis, right, if for completeness, it's the same as before. If the two inputs are in the code, then the combination will be in the code. And since the honest prover commits to the same combination, the quotient will also always be in the code as well. Now for soundness, again, it's the same as before. If either of the input vectors are far from the code, then the proximity gap guarantees that the combination is far from the code. And now letting U be the unique code word, which is delta close to the recommitment F, if it exists. We know that U is going to be delta far from the random combination, right? Because this random combination is delta far from the code. And therefore, with high probability, the quotient of the new oracle by the values computed from the old oracles will be delta far from the code. Okay, and then we're happy.
Really, there are two cases, right? There's the case that F0 and F1 or F1 are far, and thus their combination is, and thus right. But they could also be close, and then F just be a close to a different code word, something like that, right?
Yes, but sorry, could you say that last sentence again?
So it could happen that F0 and F1 are close to the code, or let's say they're even code words or something, right? And then their combination is of course also close, but then F could just be close to a completely different code word. I mean, that's another thing the prover could do badly, and which would also get caught. In other words, it looks like you're only analyzing the case where F0 and F1 are far. There's another way for the prover to be malicious, which is inconsistency.
Sure. Yes. Yes. I guess I've kind of overlooked this, but in the slide here, but kind of you will always be, since the combination is far from the code, any possible code word, it will be far from any possible code word, regardless of what the prover chooses.
If F and F0 or F1 are far, but again, that's just one way for the prover to be
Sure.
bad. The other way is for them to be close, and then for F to be close to something else different, a code word different than the one that their combination is close to.
Yeah, but I guess we don't really care about this in the soundness case, right? Like for soundness, we want to assume that like the
Oh, it's only
instance is not.
proximity okay, sorry. It's only proximity that you actually care about. My bad.
Yeah.
All
So
right,
it'll
I
be a
need to
bit more
think.
interesting when we get to the main accumulation scheme. But for now, yeah, we only care about proximity.
Yeah. Sorry.
Okay. And finally, I just want to re-emphasize this fact. The verifier, its output really is a proof oracle F, which is just taken from like selected from the prover's message, as well as the scalars xi, yi, and this virtually defines G. And since G is only virtually defined over a single oracle, we've achieved compression. Okay, and all of this just generalizes to like a many-to-one reduction, not just to a 2-to-1. Okay. So let me zoom out a bit. So actually what we have already is enough for an accumulation scheme, like a non-trivial accumulation scheme. The idea is, okay, we have a Reed-Solomon proximity accumulation, like this many-to-one reduction. And then we can kind of reuse any existing initial reduction from R1CS to Reed-Solomon proximity claim, like from snarks. And this gives us an, I guess, interesting accumulation scheme, which has asymptotically fewer queries than its snark counterpart. Now, the downside of this approach is that this initial reduction still involves quite a bit of snark machinery, Roughly speaking, this initial reduction will usually correspond to some sort of polynomial IOP. And the provers, and I've kind of omitted detail here, but typically this proximity claim, the vector that we want to claim proximity to the code for, is actually virtually defined itself over like k different oracles, where the k oracles are sent in the initial reduction. And therefore, the verifier actually is making k times O of lambda queries, like O of lambda queries to each oracle in order to query like the virtual combination F. So the natural question is, can we do better? And indeed, our main result shows that we can kind of get a direct accumulation scheme for R1CS or whatever constraint system you like, where you don't have this sort of like multiplicative overhead of k stemming from like the snark machinery. And it's direct in the sense that it looks very similar to kind of existing accumulation schemes like Nova, Protostar, Protogalaxy, where kind of all the prover does is commit to the witness. Here, intuitively, all the prover is going to do is commit to an encoding of the witness. Okay. So the high-level approach is that we're going to define these things, which I call like an algebraic proximity claim. So intuitively, like not only do we want to claim that F is close to the code, a vector F is close to the code, but we also furthermore want to claim that F is close to a valid encoding of the witness. So the specific code word that F is close to decodes to a valid R1CS witness. Right, so recall that W is a valid R1CS witness if this matrix equation holds, where Z is the concatenation of the instance and witness vectors. And what we can do is we can kind of define a subset of the code, which I call like the subcode C sub X, which consists of all of the encodings of valid witnesses, valid R1CS witnesses. Okay. And if we could construct a many-to-one reduction for algebraic proximity claims, so of the form that F is delta close to C sub X, then we're done. I claim that we're done. Like we have a very cheap initial reduction to an algebraic proximity claim, and then we can just run this many-to-one reduction. Okay. So actually what we're going to work with is like a compressed version of these algebraic proximity claims, which kind of batch together all of the all of the R1CS constraints. So for each row of all right, so like let AI be the ith row of A, the matrix A, and let BICI be the ith rows of the matrices B and C, analogously. What we can do is we can define this polynomial, which you can just imagine as like batching all of the R1CS constraints by taking a random combination with R. And the point is that if that W is a valid R1CS instance or R1CS witness, if and only if this polynomial, if you fix the X and W, is identically equal to the zero polynomial, because each coefficient of this polynomial would just be zero. Okay. And now we can define like this subcode C sub RXE, which consists of all valid encodings of W such that P of RXW is equal to E. Okay, so intuitively, you can just think of this as a compressed version of the subcode that I talked about in the previous slide. And now our goal will be to construct a many-to-one reduction for these algebraic proximity claims. Okay. So the initial reduction is now quite straightforward from R1CS to an algebraic proximity claim. So the prover gets the R1CS instance and witness, the verifier gets the instance. And now all the prover is going to do is it's going to send in the encoding of the witness as an oracle F. And the verifier is now going to just sample random challenge R. And it's going to output the claim that F is delta close to this subcode C sub RX0. Okay, so let's analyze this. So for completeness, if W is a valid witness, then as I said before, this polynomial, once you fix X and W, is identically equal to the zero polynomial. And therefore, no matter what random challenge you choose, F will be in the induced subcode. Okay. Now for soundness, if X is not in the language, then there's no satisfying witness. So again, like letting U be the code word, which is delta close to F, if it exists, then P with high probability, or I should say this polynomial is now identically not equal to the zero polynomial, right? Because the decoding of U cannot be a valid witness since X is not in the language. And with high probability over the choice of the random challenge R, F will be delta far from this subcode. Okay. And again, it doesn't, here I'm just assuming again that the delta is at most the unique decoding radius of the code. Okay. So with that, let's get to our main construction, which is this accumulation scheme, this many-to-one reduction for algebraic proximity claims. So, okay, we have two input claims. First, that F0 is delta close to some subcode, and also that F1 is delta close to some subcode. And we're going to follow kind of this, the accumulation strategy according to Proto-Galaxy, but really like, I want to emphasize that this is not really specific to any one folding scheme. You can kind of instantiate this sort of idea with things like Nova or Protostar or other things. But here we're just going to use Proto-Galaxy's rough accumulation protocol as the kind of skeleton of the construction. So we're just going to interpolate our inputs. We're going to just define polynomial to interpolate Rx, the witness, and the error value E. And then Proto-Galaxies basically says we can run a univariate sum check for this, this polynomial identity claim. So it's kind of a univariate sum check. And this yields a new claim that this composition, PRXW, evaluated at alpha, is equal to some new value E, where alpha is randomly sampled. Okay, so I've kind of glossed over a lot of details here, but really this part is not important to our construction. Like I would view this more so as like kind of Proto-Galaxy's protocol. And the observation here is that this new claim looks like a new algebraic claim. And what we can have the prover do is we can have the prover recommit to this new witness. And by linearity, you can actually see that this is a random combination of the input code words F0 and F1. And the verifier is going to output the claim that this new oracle F is delta close to the subcode induced by the new sum check claim. Okay. So the other thing that we have to do is that we need to enforce consistency as before between the virtual combination 1 minus alpha times F0 plus alpha times F1 and the prover's recommitment F. Because right now, in the previous slide, there's no reason for the prover to have to recommit to the actual combination. And so naturally, we could try to just use the quotienting strategy that we had before. But the issue is here that the quotient doesn't really play well with algebraic proximity claims, in the sense that even if this vector F is a valid code word in this subcode, it doesn't necessarily mean that its quotient is also in the subcode. So in some sense, like the quotient does not preserve the algebraic structure that we're checking. So the way that we solve this problem is to, in some sense, accumulate the proximity claims for quotients separately from the main algebraic proximity claim. And in particular, the verifier is going to output both an algebraic proximity claim that F is delta close to the subcode, as well as a standard proximity claim that the quotient of F at some random points is delta close to the overall Reed-Solomon code. Okay. So if we look at this construction in action, we're going to have a 2-to-1 reduction for both algebraic proximity claims and standard proximity claims simultaneously. So the verifier receives 4 claims in total, 2 algebraic, 2 standard. And then it's going to run the sort of Proto-Galaxy style accumulation scheme to reduce or compress these 2 algebraic claims and the prover is going to recommit to what the random combination of the two input vectors should look like. Okay, and then the verifier outputs this proximity claim for f being delta close to the new subcode. And additionally, the verifier is going to output, it's going to forward both of the initial standard proximity claims as well as this new proximity claim for the quotient of f. And now what we can do is actually we can run our original many-to-one reduction for Reed-Solomon proximity claims to compress these three things into one. Okay, and as a result, we end up getting a single standard proximity claim and a single algebraic proximity claim, which we can continue to accumulate in the future. Okay. So completeness is fairly similar to the protocols I described earlier, so I won't really talk about it. Instead, I want to really focus on this a sketch of the soundness proof, which I think is a bit more interesting. So the point is, if either, all right, so first of all, if either G0 or G1 is delta far from the code, these are like the input standard proximity claims, then our proximity accumulation scheme guarantees that the new vector G will be delta far from the code. So that case is handled. We also need to consider the case where either F0 or F1 are far from their respective subcodes. So these are the algebraic proximity claims. Then what we can say is that the proximity gap plus the sum check guarantees that this random combination of the input vectors, F0 and F1, is delta far from this new subcode. Okay.
So do you need
Now,
oh, sorry. For the second bullet point, do you need to use like a proximity gap result for like general codes, like not the Reed-Solomon one?
no, yeah, so we rely on just the proximity gap for Reed-Solomon codes. In some ways, yeah, I guess the proximity gap for these subcodes would naturally follow from that. But yeah, it's a bit, the analysis is a bit more complicated because you kind of have this, the random challenge alpha is both functioning as a proximity gap challenge as well as the sum check challenge. So you need to like.
Oh, you're saying, yeah. Oh, sorry to, yeah. Okay, you're saying in general a proximity gap result. It also implies the same result for any like subspace. Oh, okay, yeah. Then that makes sense. Thanks.
Yeah. So actually, like our yeah, exactly. Okay, so there are two cases now. First of all, if the new oracle that the prover committed to is far from the subcode, then we're done, right? Because this new instance is invalid. So now we just need to consider the case where the prover is trying to cheat, right? The prover is trying to cheat by recommitting to some new vector f, which is actually delta close to the subcode. So in this case, letting u be the code word, which is uniquely delta close to f, we can observe that u is actually a member of this subcode, CRXE. And since the random combination is delta far from the subcode, we know that u must be delta far from this random combination, right? And now we can just use the fact that the quotient in this case must be delta far from the code. And therefore the proximity accumulation guarantees that G will be delta far from the code. So to summarize, kind of, we've taken I've highlighted in red all of the possible bad inputs. And we showed that in all possible cases, our reduction leads to a blue, like what's highlighted in blue, which corresponds with the new input being, the new output being far from the code. Either the standard proximity claim it does not hold, or the algebraic proximity claim does not hold. Okay.
Sorry, I have a question.
Yeah.
So regarding this proximity gaps with respect to this like subcode of R0, X0, E0 using sum check. So in that case, do you still have the same bond like a regular Reed-Solomon code, like the Johnson bond, or is it actually the same bond that, for example, has base fold, which is double Johnson bond? So like,
Yeah. Okay, so I guess right now, the soundness sketch that I've put up here, I'm assuming that delta is almost the unique decoding radius of the code, first of all. So in terms of the soundness error, because we're using the proximity gap, we're using the same challenge for the proximity gap and the sum check. The overall soundness error of this step would be like the sum of those two errors. So it'd be the sum of the proximity gap for just Reed-Solomon codes. Don't worry about the subcode business. Plus the error incurred via a sum check.
I see. So you are directly using the unique decoding bound, not Johnson bound at all. Just the safest bound you are saying.
In this slide, yes.
Okay.
I'll get to optimizations on the next slide.
Okay. Yeah. Thank you.
Yeah. Okay. So yeah. So we also have some optimizations that we talk about in the paper. So the first is, yes, like so far in this talk, I've only focused on delta being within the unique decoding radius of the code, but we can also support a proximity bound delta up to a list decoding radius of the code, assuming that a suitable proximity gap exists. And in this case, it's a bit more complicated, but roughly it's still the same as before. The soundness error is just the proximity gap error for Reed-Solomon codes up to like that list decoding radius, plus the sum check error. So there's no special error corresponding to the fact that like we're talking about subcodes. Really, the fact that we're talking about subcodes is just related to the sum check error. Okay, I don't know if that answered your question, Binny.
I guess the question is, so basically you are using the best list decoding bound radius in the
Yeah,
result?
I mean you can instantiate with yeah, whatever proximity gap result.
Yeah, I'm not fully sure I follow because, for example, base4 doesn't have the best bound compared to Fry because the sum check. So the best result we can get is like a 1.5 list decoding bound, not
Oh, I see. Yeah, so okay,
strong.
so there are two options. So in the paper we like okay, so the protocol is more complicated. Basically, we need to do like some additional rounds of out-of-domain sampling in order to get the full bound. The other option is to rely, and this like I guess slightly makes the protocol more ugly and I guess a bit less efficient. So I would say like we can talk about this later as well.
Yeah.
But then the other option is you can use like some sort of mutual correlated agreement, which is a more recent notion of proximity gap. And that would also work. But as you said, right, like I don't know if we've actually proved like mutual correlated agreement up to list decoding bound for Reed-Solomon codes.
Yeah.
But in that case, if you assume mutual correlated agreement, then the protocol is a lot simpler. You just do like one round of out-of-domain sampling, similar to something like Stern.
I see. Yeah, that makes sense. Thank you.
Okay. Okay, the other optimization is that we can kind of reorganize our protocol so that the prover sends the oracles F and G simultaneously as like a single interleaved oracle. And the point here is that we can kind of reduce the Merkle tree openings once you compile this interactive oracle reduction to a standard reduction. Okay, but yeah, both of these things, you can just see the main paper. Okay, so finally, I just want to give a very high-level comparison between our hash-based accumulation scheme and the prior best-known approach to constructing like full-fledged unbounded hash-based accumulation, which would be just to use a snark, like the baseline solution. Okay, so if you were to use a snark, then your initial reduction from R1CS or whatever constraint system to a Reed-Solomon proximity claim would consist of like the prover sending like, let's say, k oracles, where in practice, like k is like at least 3, let's say, followed by a Reed-Solomon proximity test, where the prover sends some additional smaller oracles, which don't really matter. And the verifier makes O of lambda queries to each of the K oracles, plus an additional O of lambda times log n queries. Okay. Now in our accumulation scheme, it's both of the reductions are different, right? So our initial reduction is R1CS to an algebraic proximity claim, not a Reed-Solomon proximity claim. And in this case, the reduction is quite simple. The prover literally sends one oracle, just a commitment to the encoding of the witness. And then we also have like this algebraic proximity accumulation, like this many-to-one reduction, where the prover sends one oracle if you incorporate the optimization. And the verifier only needs to make O of lambda queries to its two inputs. Okay. So as you can see across the board, our prover is sending less oracles, right? Sends two in total between the reduction and the initial reduction and the many-to-one reduction. And we have like a asymptotically and quite concretely smaller accumulation verifier, due to the fact that in these snarks, you typically have like many oracles that you need to combine in order to run a proximity test over the virtual combination. Okay.
So I have one more question, sorry.
Sure.
Yeah, it seems that there are also an intermediate solution you mentioned initially, right? Well, initially you do a reduction from RCS to RS proximity claim, and then you use your like your arc folding scheme or reduction of knowledge to do the rest instead of using stir or whir.
Yeah.
So how about that one? Like what's the performance comparison for that kind of solution?
Yeah, so this is like this sort of approach is also what is looked at in like the concurrent works, like this many-to-one reduction for Reed-Solomon proximity claims. Yeah, so I guess the cost would look somewhat similar. So first of all, the initial reduction would be the same as for the hash-based snark. So the prover sends K oracles. And then in that case, in the proximity reduction, the many-to-one reduction, the prover does not need to send any additional smaller oracles. It actually just sends one oracle. And then the verifier would make O of lambda queries to the K plus one oracles. So the K oracles from the initial reduction and then the additional oracles sent by the prover in the many-to-one reduction. So it'd be K plus one times O of lambda. And then there wouldn't be this additional lambda times log n queries.
I see. So essentially, if K is larger than 3, you still think the rightmost scheme is the most efficient one. That's yours.
Yeah, I would say that like if you were to just use the intermediate solution, like you would get some savings. It depends on like what K is, and it depends on how the parameters are concretely set in terms of this log n factor. But I think it's clear. Like morally speaking, I think this accumulation scheme is like it's a proper accumulation scheme, whereas the other one is more of a this thing on the right is more of like a folding scheme, whereas the intermediate thing is I would consider less useful. Okay. Cool. So just to wrap things up, so in this paper we gave the first full-fledged in terms of unbounded depth hash-based accumulation scheme, which achieves a asymptotically smaller verifier than the baseline approach, which would be to use a hash-based snark. And one of the core components in our protocol is this many-to-one reduction for Reed-Solomon proximity claims, which relies on a quotienting strategy that's inspired by stir, but used for a slightly different purpose. Okay, and then we use this many-to-one reduction for Reed-Solomon proximity claims to bootstrap to a many-to-one reduction for just general algebraic proximity claims. And this is what lets us like get something more interesting than just hash-based snarks. Okay, and finally, I just want to mention some upcoming work of ours, which should hopefully be on ePrint soon. So in that work, we kind of tackle this question where, so first of all, like ARC is very specific to Reed-Solomon codes because this quotienting strategy is unique to Reed-Solomon codes. So I guess a natural question would be, can we do some sort of accumulation where you can instantiate the linear code with any code of your choice, for example, like a linear time encodable code? And if so, can you also make this resulting accumulation scheme linear time? So yeah, this is we address both of these questions in this new work, which hopefully should be online soon. And yeah, that's all I have. Thanks.
Thank you very much, William. Yeah, maybe you'll come back for to present this new work in a few months. That would be fun. Before we wrap up, does anyone maybe still has a question about William's presentation? Maybe I'll give you a few seconds. I know we had a few during the presentation, so I expect that was kind of it, but
So one question, do you have how do you think in terms of practical performance, this compares to this new work you just mentioned?
Yeah, so I would say that the new work is a strict improvement because you could always instantiate the new protocol with Reed-Solomon code. And then for other reasons, it's the verifier makes the same number of queries, but in terms of field operations, it's smaller. And the prover also is linear time outside of like encoding. So Reed-Solomon encoding takes like quasi-linear time, but the rest of the protocol in this new thing, the prover would take linear time as well. So I would say that this new work probably just supersedes this one. But in terms of like comparison between using a Reed-Solomon code and like a linear time encodable code for accumulation schemes, it's less clear to me what the performance difference would be. I mean, it's a bit hard to say, right? Because like typically like the linear time encodable codes start to outperform Reed-Solomon codes in terms of prover time. Like you need the size of your statement to be large enough for the asymptotics to kick in.
Well, this recent like Blaze one, I think it's supposed to be better than Reed-Solomon for any n or reasonable
Oh,
n.
really? Okay.
I mean, I think they say in the paper the encoding time is 8n. So yeah.
Okay, yeah, I guess I can't speak on that. Oh, so maybe they're saying that okay, so if indeed it's true that like this encoding time is just better, and you also factor into okay, so the other issue is that like for example, this Blaze code, the distance is like not is worse, right, than like a Reed-Solomon code for the same size. So you also have to factor that in. But okay, assuming that the encoding time, if you control for the distance, is better, then yeah, the new protocol should just work very nicely. I guess I should also like there's like another nice tidbit. In our new work, we actually try to do straight line extraction, even if the underlying code does not have like an efficient decoder, like it is for a lot of these practical linear time encodable codes. So there's kind of across the board no drawbacks to doing that then.
How much of this have you implemented? Is other kind of performance conclusions, are they theoretical, or have you done experiments?
About this paper, or
yeah, this paper. Well, both really.
So this one, we don't have an implementation. I mean, in terms of like the prover costs, I think part of it is that it would look very similar to, you can imagine that our prover is kind of running a subset of something like stir. Like it's running the first round of stir and nothing else.
Yeah.
And you can think of the verifier as kind of being a subset of the stir verifier. So if you just compare the two, then like clearly the subset will be better. The question is how much better.
Yeah. The question was directed at how much better. I believe you is better.
Yeah. So we don't have an implementation yet for the new protocol. This is something that I want to work on but at the moment we also don't have an implementation for that.
So in the new work, does that mean you do need proximity gaps for general codes, or how does that work?
Yeah, so you need a corresponding proximity gap for the code. So this exists for all codes, obviously with like a worse bound, but
So your proximity parameter is limited to p/3 in the case, right?
Yeah, so I mean, there's also been some more recent results that actually show proximity gaps past the unique decoding radius, like up to some like 1.5 Johnson bound or whatever.
For general
So
codes?
yeah, for general codes.
Can you share that?
Yeah, there's two. One is from a DOS. It's called Khatam, Khatam. And the other one, unfortunately, I don't remember the authors, but it's cited in Khatam. So both of them, I think they get slightly different results, but the other important thing is that in our new work, we also rely on mutual correlated agreement, but both of these works also prove that. So it's like a stronger version of a proximity gap.
So proximity gaps and interleaved codes. ICR 2024-3051, is that the one?
Yeah, I can just check right now.
No, Daira, I think that's my paper with Angus. That is not that does not have anything to do with beyond
Okay.
the unique decoding radius. Actually, the point there is for tensor combinations. I can explain, but it's a
no, it's the wrong
separate
paper.
Yeah.
Yeah, okay, this is okay, I can post the links in the Telegram after this call.
Thank you.
Sure.
Perfect. Sounds good. So yeah, thank you everyone for joining, and thank you very much, William, for the presentation. And yeah, I guess we'll see you guys at the next session. Thank you very much.